So I'm gonna, So I'm just going to let's do this. Do it this way. Okay, Control C. And if it doesn't know what I want, I try to do here. All right, so I'll do that. I'll come up here and call this the new day. And do that, and that should drop that in for me. Oh, perfect. Okay. But that didn't give me what I wanted because I didn't actually need anything from that page. I need it from this page. I promise I'm almost ready. It shouldn't have been this complicated, but I did a good job of making it that complicated. Okay. All right, so I think for some of us, some of the issue was asking for all these different notations. So first thing first, some of these notations you can't really do for all the problems. So if that's the case, just leave it blank, it's fine. So for example, if you have a domain or range, a set that is finite, you can't write an inequality for that, and you can't use interval notation for that. So for like 1 and 2, and then 7, 8, 9, or I'm sorry, 8, 9, and 10, you can't do those parts. There's nothing to do. Just leave it blank. It's fine. No big deal. Okay? If you do have an infinite domain or range, you should be able to write all three of these in all three ways. So let's say, for instance, that just we have a domain, and we've mostly wrote things using interval notation in class, right? Sergio, are you happy? Okay, so I'm going to write just an example of a domain that was in interval notation, and we'll translate it to the other two notations. Because I feel like if we do that once, then you should be good, right? Does that feel okay?
Yeah.
All right. So let's say our domain was like the interval 2 to 5. Okay? So as an inequality, this is just 2 less than x less than or equal to 5. Right? The parenthesis means strict inequality, and the bracket means the or equal to inequality. And the lower bounds are just the bounds for our inequality. Okay with that? All right. So for the set builder, these are just, this is a domain, so it's just a set of x's. So we'll have the set of x's such that, and our rule just be the inequality that we used for the as an inequality. There's like nothing, I mean, the two are virtually identical. It's just a little bit of notational difference. But what you would do to write them out, you know, like the hard part is the same for both of them. It's just an inequality is the rule, which would be the same as writing the domain or range as an inequality. And the only reason I'm asking you to write these all three ways is oftentimes on like a standardized test situation, you don't know which way they're going to represent things, whether it's going to be an interval or an inequality or like a set or what it's going to look like. So I just want to get you a little bit comfortable here in the beginning of like seeing these things in different representations, so that if you're doing something like that, you get to a question like, I don't even know what this means. I've never seen this notation before. That's not you, you know? Hold on, it's Mackenzie, right? Okay. This, I just absolutely made this stupid thing up. So like, this doesn't correspond to any of the problems. Talking to Sergio on what he was looking for, it sounded like if you could, he was okay getting like an interval notation answer for something like one of these. And if he had that, can I then translate it to the other ones? Is what I took as what he really needed. Was that accurate, Sergio?
Yeah.
Okay. So that's what I did. I just made up an interval, and then we translated to those other two forms. It had nothing to do with any of the problems here on the page. Zach,
Yeah.
Okay.
So for like number 10 where it's a finite set,
Yes.
there would be no interval or inequality and the set would just be x colon and then we list the numbers.
Or you could just write just no x colon, you could just list the numbers.
You have to put them in like parentheses or just list them?
You could just list them. So just like something like that. Now, if you did x colon and then you wrote x equals and you listed them, like that's fine. Like there's nothing wrong with that, but like you don't need to do it that way because since it's finite and we're labeling it as a domain, it's pretty redundant. But it wouldn't be wrong to do what you described as long as it was like x colon and then x equals your list. And you can just separate it with commas would be fine. But that would be appropriate as well. Edmund? Ed? Eddie?
Yeah.
Okay.
So for the builder notation, say you had like 4 numbers in the domain.
Okay.
Would you have to list them? Would listing every single one still count for the notation, or would you have to pick out the?
No, like that would be fine. For a finite? Yep.
Oh, but if it's infinite?
If it's infinite, you can't list them all.
Yeah.
Right? Then you'd have to use an inequality to say everything like between these two values or whatever. Does that make sense?
Yep.
Okay. Yes. Tell me your name though.
Ava,
Ava. Thank you.
when you go over interval notation,
Sure. Do you want to do it for a specific one of these?
let's see. How about 3?
3. Okay. So 3 was actually one that I think we did this exactly in the homework, or in the notes, excuse me. So I'm going to go back and just reference that if that's okay. Okay. Probably this day. Or maybe we didn't. Did we not? Oh, maybe not. Okay. Okay. That's fine. We can talk about it for sure. Okay. You know, sometimes you can't remember what you did as an example in one class and not the other class. You know, you do this so many times because I really have all 3 of the classes I'm teaching. All 6 of the sections are kind of doing the same stuff right now. So it's between one class to the next, it's hard to remember sometimes what you used as an example in one class versus another class. All right. So one way is you might have recognized from geometry that this is the equation for a circle. That the equation for a circle is of this form. So what you have here is a circle whose center is, in this case, that's 0, 0. And its radius is 1. So you might have remembered this from geometry. It's possible. Okay, so if you did, I would use that to translate that into a picture, and I would use the graph. If you didn't, which again, like it's the second week of school or whatever, geometry was a long time ago, this would have been like, I don't think a major piece of geometry would have been like you spent a couple of days maybe doing this and then you moved on to something else. And like, if you didn't remember this equation or this form, I wouldn't fault you for that at all. Okay, so if you're like, you tell me we did this, I believe you, I kind of maybe remember this, but like, I would not have come up with this if you'd given me a long time to think about it. That's perfectly reasonable. So let's use some common sense then, okay? So what I'm going to notice straight away is that x squared and y squared, because they are squared, they always have to be greater than or equal to 0, right? I know that something squared can never be negative. That's like a basic, like pre-algebra fact. Okay with that, Ava?
Yes.
Okay, so what I'm going to do is I'm going to just then, for example, if we're going to do the domain first, the minimum value that y can have is 0. So let's just pretend that y is 0. That's going to simplify us down to x squared is equal to 1. Are you okay with that?
Yeah.
Okay. In the instance that y is 0, what is the biggest value x can have then? Yes. Fantastic. We can also have another value, though. What would the minimum value for x be? Not 0. What did you say, Edmund? -1, right? Because 1 or -1, if we square it, still gives us 1. Everybody's okay there. Now, if I had any number between -1 and +1, and I square it, it's still going to be less than 1. Agreed? Because I know that if I take like a 1/2 and I square it, it gets smaller. It turns into 1/4, right? Any number that's not, or between -1 and +1, when we square them, they get smaller. Everybody's okay with that? So what I've found here is my upper bound for my interval and my lower bound for my interval, right? Because I know there's no value of x that could get smaller than -1, because if y was greater than 0, x can't be -1 because you have something that's bigger than 0 plus 1, which is going to be bigger than 1 and not satisfy our equation. Does that make sense?
Yeah.
Okay. So my value for x then, my lower bound is -1, and my upper bound is +1. So when I write my interval, I always have the lower bound first and the upper bound second, separated by a comma. Is that okay?
Mm-hmm.
And now to decide whether I get a bracket or parenthesis, I'm going to think about, does -1, in this case, does that actually represent an ordered pair in my relation in my function? Is that the x coordinate of some ordered pair that is a member of my function? So I know right here what I have, because I have y equals 0 and x equals -1. I know -1, 0 is a member of the set of xy such that x squared plus y squared equals 1, because if I plug these two values in for x and y, that equation is satisfied, right? You okay there?
Yeah.
Now, if this was, say, for example, like a strict less than instead of an equal sign, like x squared plus y squared is less than 1, there I would use a parenthesis, because if I put in -1, 0, that's not actually a member of that set. It doesn't satisfy it because you'd have 1 less than 1, which is not true. Does that make sense?
Yeah.
Okay. And if I do the same thing then with the point 1, 0, that would also be a member of my relation or my function. It's not a function in this case because it's a circle, but it's be a member of the relation. Are you happy with what we did there, Ava?
Yeah, thank you.
Yeah, you're welcome. And for the range, you could do it the same way, right? Since it's x squared plus y squared equals 1, there's no real difference between the domain and the range,
Okay.
because you do the same trick. For the range, you just let x squared or x equals 0, and then the y values would be the upper and lower bounds would be still -1 and +1.
Okay, thank you.
Does that feel okay?
Yes.
Okay. So again, like the idea here as we go through these algebra courses is we want to kind of build out our toolbox of things that we recognize. So like these little forms like, oh, I recognize this is going to be it's going to look like a circle, or, oh, this thing's going to look like a parabola, or, oh, this thing's going to look like a line. The more we can do that and add to our repertoire of things that we recognize, the easier things like this become, because you look at the equation and go, oh, I know what the graph of that looks like, so I can use that information to find the domain and range. I don't have to do like a common sense like analysis like this that takes a little bit more time and you have to think a little bit harder about. You'd like to just automatically see the thing and recognize it as, oh, it's one of these things, so I know it's going to look like this. But we're not there yet, right? Which is fine. But that's the hope as we build through this semester, to kind of build out that toolbox a little bit. Mackenzie. Okay. So, right. So let's do this then, right? The function part we have to worry about. Does the same x go to two different places, right? Agreed with that, Mackenzie? Okay. So let's pick an x and then solve for the y and see how many answers we get. And we should probably do this more than once because, well, you know, you never know how many times or how many places you're going to have that vertical line test going. But if you didn't recognize this as the equation of a circle, which I assume is kind of the motivation behind this question, right? Okay. So pick a value for x. Or I'm sorry. Yeah, pick a value for x. Okay, so 2 isn't in the domain, right? You need to pick something from the domain. 1? Okay. So if we pick x to be 1, we have the equation x squared plus y squared equals 1. So we plug 1 in for x, and then 1 squared is just 1. And then we subtract 1 from both sides, and then we square root both sides, and we have y equals 0. And we get just one answer, which is good, right? That would imply to us that maybe this is a function, but we should do more than just one check. Because if it's a function, every value for x that we do this for should give us just one answer. If it's not a function, all we need is one instance where this doesn't give us one answer. So let's do it. Let's pick another value. Let's do 0. How about that? Right? That's also in there. In general, the upper and lower bounds are sometimes not the best choices. Now, certainly there's no reason that you would know that right from where you're at. But I will tell you right now that oftentimes the ends of the domain are not the places where you have problems. So for sure, those are not bad choices to check, but we should check stuff from the middle of the domain also. So again, if we pick x to be 0, so 0 squared is just 0. And then y squared plus 0 is still just y squared. And we square root both sides, and we get y equals the square root of 1, which is just 1. But you've forgotten something because we squared root both sides of an equation. We also need to include a plus or minus. So this right here is telling us that we have both the point 0, 1 and the point 0, negative 1. And that's our evidence for that this is not a function. And Mackenzie, literally any value of x other than 1 and negative 1 that you pick, you're going to get this thing happening. Because when you square root both sides, you get that plus or minus, and the only place the plus or minus doesn't give you problems is if there's a 0, right? If it's plus or minus 0, which is literally what's going to happen with 1 and negative 1. But any other value of x would get you this same thing happening. Is that okay? Yes. What's your name? Amy. 8. Mackenzie, you're happy with what we did there, though?
Yeah.
Okay. Okay. Is it just so that you can't read the letter or the names?
A little bit more.
Okay. So if you can't read what the names are, like, as long as you have like a letter, like the first couple of letters close, I'm fine with that. Like, you just have to do enough for me to be convinced that you knew what you were doing. Like, I can't read what they say either. I can kind of guess, like, Maria, Jose, Sarah, Jenna, maybe, and I don't know, Austin. I can't even tell. And then what's that say? PO something, PowerPoint. I don't know, rappel, handshake, oral presentation. Some of these things I really can't read either. So if we're just looking for a domain, or looking for if it's a function or not, everything in the domain is used, right? And each domain only goes one place, so I know it's a function. My domain would just be like a list of the things in the domain. And the range would just be a list of the things in the range. And because this is a finite set or a finite relation, there's no interval notation for me to write it this as, or no inequality for me to write this as. It's just this list. Well, because it's a mapping diagram. So the mapping diagram is just each ordered pair is represented by an arrow. We have, 5 arrows, so there's 5 ordered pairs in this, and that's it. That's finite, right? There's not an infinite number of arrows. In fact, you couldn't even draw an infinite number of arrows in a mapping diagram if you wanted. The only places where you can have an infinite number of ordered pairs is with a graph, right? If you have anything that's connected, that's an infinite number of ordered pairs. Or with an equation, because oftentimes there's going to be an infinite number of ordered pairs that satisfy an equation. But if it's like a set of ordered pairs, well, unless we use that fancy set builder notation, it's finite. If it's just a list of ordered pairs, or if it's a relation which just has like finitely many arrows, does that feel okay, Amy? Surgical.
What would the
Oh, what we just did? Okay, so we have the domain there as -1, +1 with the brackets, right? So the inequality, because they're both brackets, the inequalities will be both less than or equal to. That's it. Is that okay?
Yeah.
So again, the upper and lower bound for the domain is telling you the upper bound and lower bound for your inequality. And the or the bracket just tells you or equal to, and the parenthesis would tell you just less than. And that's it.
we chose those?
This we discovered specific to number 3. We figured this out for specifically to for number 3. This is a specific answer. Is that what you're asking?
No, I was saying I knew it was for that. Yeah, so when we pick our domain for number 3.
So there's not a picking. We figured it out exactly that everybody should have that answer. Maybe I'm not understanding what you're asking. The word pick.
Yeah, no.
I
I have it all written down.
Okay. Yeah, so what we did is we did a little bit of an experiment to figure out what the domain was that involved picking some x's. But those x's the way we did that is we're trying to figure out the upper and lower bound for this so we could write down the domain. That's what the picking involved, was us figuring out the upper and lower bound for the domain.
Oh, I meant when you said domain, let y equal 0.
This is me trying to figure out if it's a function or not.
Oh.
So we picked those, just doing an experiment to see if, no, I'm sorry. So this was me trying to figure out the upper and lower bound. So what I noticed was, since both these things are squared. They both have to be greater than or equal to 0. So the minimum value either one of them could be is 0, right? So I said, okay, we're doing the domain, so let's pick y to be the smallest thing it could possibly be, which is 0. So at minimum, this is going to tell me the upper bound for x, the biggest thing x could be, right? But it also ended up telling us the lower bound because there are 2 answers for that. Does that make sense? Yeah. Okay. So that's what I was doing there. So that was what the picking was about, was me trying to figure out the upper and lower bound for the domain. Okay. Do we feel better about this assignment? Good enough to where you could finish the rest of it if you still had things to finish? Okay. Again, the homework doesn't have to be perfect. I'm looking at completeness, not necessarily correctness. As long as you have reasonable work and have attempted most of the stuff, it's fine. Okay? Today, what do we still need to talk about? What did we talk about last time? I guess I should ask. Okay, so domains and ranges and function or not function. Okay. So today, we've been talking about how to tell if something's a function or not, and then what its domain and range are, right? And in fact, most of the rest of this year, we're going to be spending talking about these different kinds of functions. So one of the things that we're going to want to do is we're going to develop a language that we can use to kind of compare and contrast different types of functions. So what we're going to do right now is we're going to start developing that language and talk about some attributes that functions can have and how we can kind of compare them. Okay? Just like if you learn about mammals in biology, you're going to start learning about the attributes of mammals, and so you have things to compare and contrast about them, like whether their size, or how many, like how long they're pregnant for, or like how many fingers and toes do they have, or, you know what I mean, digits on their appendages, I guess is maybe the better way of saying it, because I don't think that like elephants have fingers and toes, but you know what I meant. Okay. So attributes of functions. So the first attribute we're going to talk about is positive, negative, and 0. So what we're talking about here is we're talking about when is the function positive, negative, or 0. What does this really equate to? Well, from a graphical perspective, positive means we're above the x-axis. Negative means we're below the x-axis. And 0 means we're on the x-axis. Okay with this idea? So if I give you a graph, you should be able to identify for me the parts of the graph that are positive, negative, and 0. Everybody okay with that idea? Now, how do we report that? We report that by giving those parts of the graphs x coordinates in the form of an interval, more often than not. Okay, so we'll describe the x values where the graph is above, below, or on the x-axis. So if I look at this picture that we've just drawn here, how many parts of the graph do you see that are positive? 2, right? We see this part here, and we see this part here. Everybody agree with that? Let's add in some coordinates here so that this makes we can talk about this a little bit more intelligently. So if I'm going to write down the interval over which this graph is positive, I'm going to need two intervals because there's two sections of this graph that are positive. Everybody agree with that? So if I look at the leftmost interval, what is the lower bound on that leftmost interval? Where does that interval, what point does that interval begin at? -2, 0, right? Everybody agree with that? Now, if we're writing down an interval, the only thing we care about are the x values. So my interval is going to start at -2. And then it continues to what point? 0, 0. Again, all we care about is the x value. So my interval goes from -2 to 0. Is everybody okay with that? Now I need to decide whether I should have a parenthesis or bracket on this interval. So if I look at that point, -2, 0, is that point above the x-axis? No. Where is it located? On the x-axis. Because it's not above the x-axis, we don't want to include it with the positive parts. So we're going to use the parenthesis because the point -2, 0 is not above the x-axis, so we don't want to include the x value of -2. We'll do the same thing for 0, 0. Is this above the x-axis? No, so it'll also get a parenthesis. Is everybody okay there? Okay, and then we'll use that union symbol to attach our next interval. So that's just like the letter U with no tail on it. If I look at our next interval, what point does the next interval begin with? 3, 0, but all we really care about is the x-coordinate, so the 3. And then what point does that interval end at? Really positive infinity, right? Because it keeps going to the right forever, because we have an arrow at the end of the graph. Now the infinities we know always get a parenthesis on it, so we don't even have to think about that. How about the 3? Should that have a parenthesis or a bracket? Should have a parenthesis because the point 3, 0 is not above the x-axis, right? That's what the positive stuff means. It has to be the stuff that's above the x-axis. Okay. Let's do the negative parts now. How many negative parts do we see? I see 2 as well. I see this part right here. And then I see that part right there. So if I look at the leftmost negative section of the graph, what point does that section begin with? Negative infinity. Good. And it goes until what point? -2, 0, but we only care about the x-coordinate, so we're just going to write down a -2. Should the -2 get a bracket or a parenthesis? Should get a parenthesis because that point -2 isn't below the x-axis. Remember, that's what negative means, is below the x-axis. Okay, well then we'll use our union and connect the next interval. The next interval begins at what point? 0, 0, but all we care about is the x-coordinate, so we'll write 0. And it ends at 3, 0, but all we care about is the x-coordinate, so we'll write 3. Is everybody okay there? Again, when we're writing these intervals for positive, -0, we only care about the x-coordinate, right? It's from this x to that x. All right, so the point 0, 0 should get, the 0 should get a parenthesis or a bracket. Parenthesis. And the 3 should get a parenthesis. Okay. How many places on the graph do you see that are, or how many pieces of the graph do you see that are 0? I see 3. I see one right here, and one right here. Does everybody agree with that? Now that we pointed out. Now, notice on those three sections of the graph, how many, do those contain infinitely many points, those sections? No, those are just single points, right? Where the graph is crossing the x-axis at a single point. So when I write my 0 set here, I don't want to use an interval notation because I don't have infinitely many points. I just have exactly 3 points. So instead of using an interval, I'm just going to use the normal set builder. And all I'm going to do is list the 3 x coordinates. So -2, 0, and 3. Is everybody okay there? Let's do one more example on that. Okay? And this one I'm going to really give you something tricky to make sure we got it, right? Sometimes the more complicated ones really kind of help focus things in, right? Okay. How many positive pieces of this graph do we see? Just one, right? That's all I see. So I just see this section right here. Okay. What point does that positive section begin at? -1, 0, so we'll start with the -1. And it ends at what point? 1, 1, so we'll again use the x coordinate, so 1 there. Now the point -1, 0, is that above the x-axis? No, so I use a parenthesis. Is the point 1, 1 above the x-axis? So we'll use a bracket. Everybody's good with that? Okay. How many negative parts of the graph do you guys see? I see 3, right? I see this one, I see that one, and I see that one. Do you guys agree with that? Okay. What point does that first negative section appear at? -5, -3. So we'll start with the -5. And then it ends at what point? -3, -3. So we'll use a -3 there. Everybody's good with how I got that? If I look at that point, -5, -3, is that below the x-axis? So that gets a bracket. How about the -3? Should I get a parenthesis or bracket? You say bracket because it's below the x-axis, right? But is there a point there? No. So what should I really put here? I should put a parenthesis. The open circle supersedes the location of the point, right? You have to have a point there in order for it to be included. If we don't have a point there, it can't even be included, even though the end of that interval is below the x-axis, but it doesn't end at a specific point, right? Everybody's okay with that idea? Okay. So then we'll use our union, and we'll go to our next interval, which begins at -2, -2, but all we care about is the x-coordinate. And then it ends at -1, 0, but all we care about is the x-coordinate. Should the -2 get a parenthesis or bracket? Bracket. Very good, because that point is below the x-axis. Should the -1 get a parenthesis or bracket? Parenthesis, because that is on the x-axis, not below. And then our last piece of the graph begins at which point? 1, -3, but all we care about is the x. And it ends at 3, 0, but all we care about is the x-coordinate. Should the 1 get a parenthesis or bracket? Parenthesis, notice that even though it's below the x-axis, it's not a filled-in circle, so that point isn't included, so it definitely gets a parenthesis just because of that. How about the 3? Parenthesis, because that point is not below the x-axis, it's on it. Okay, and then we'll do our 0, which is that section there. So it begins at 3, 0 and ends at 4, 0. The 3 should get a bracket, right? Because 3, 0 is on the x-axis. Everybody's okay there? How about the 4? That gets a parenthesis. Am I really done here, though? Did we forget something? What did I forget? There's one other 0 part of the graph right there, isn't there? So we're going to do union. Oops. Same color, though. Union. And that's just a singleton point. So I'm just going to use like the set builder squiggly brackets for that single x value. Amy? Yes. So this is 1 point, right? A section like this is infinitely many points. So if you have infinitely many points, we use interval notation. If you have finitely many points, like 1, 2, 3, 4, 20, we use the builder. Is that good? Okay. So any section of the graph that has infinitely many points, it's like a connected section, we're going to use the interval notation. But if you have like single points, and there's like 8 of them or something, or 1 of them, you use the set builder. Do we feel okay with positive, -0? Not bad, right? We just have to kind of look at the graph and identify the areas. The hardest part is getting used to the notation and writing the interval. But with a little bit of practice, it's not too bad since we've been writing interval notations for a couple of days now.
I have a question.
Yes. Go ahead.
0, 1, 3 have a bracket.
So the point 3, 0 is on the x-axis.
Okay.
So it should be included in the 0 set.
Thank you.
You're welcome. Okay. The next comparison is increasing, decreasing, and constant. So I'm going to give a rather informal definition, and then I'll explain to you the little bit more technically as it justifies to how we're going to do bracket or parenthesis on the endpoints of our interval. So increasing are the sections of the graph where we're walking uphill, as if we walk along the graph from left to right. Decreasing is we're walking downhill on the graph as we walk left to right. And constant is the sections of the graph that are flat as we walk from left to right. Now, this is a really practical and informal definition for what we mean by this. Let me just state here technically what we mean. So, for an interval to be increasing, I should be able to pick any point on that interval, and then if I pick any point to the right of that point on that interval, the slope between those 2 points should be positive. Okay? So when we talk about and then likewise, if we're still for increasing, if I pick that point and I pick something left of it on the increasing interval, the slope should be negative, right? Everybody's okay with that idea? Now, if we think about the endpoints, if I'm at the far right end, is there anything to the right of it to pick? No. If I'm at the far left end, is there anything to the left of it to pick? No. So the endpoints we're not going to include in any of these. Okay? So for increasing, decreasing constant, the ends are always going to be parentheses. So that's a little bit nice for us. Okay? I'll make another comment here in a minute, because that's changes a little bit for this the idea of constant if you take a calculus course, and I'll just mention it as kind of an aside. Let's do that. Excuse me. Got a case of the yawnies. Okay. So, how many sections of this graph do you see that are increasing? Again, think about it as the sections of the graph where you'd be walking uphill if you're walking along the curve from the left side of the graph to the right side of the graph. Sergio? 2. There's one right here, and then there's one right there. Does everybody agree with that? So let's write those intervals. So what would that first interval be? -3, 2, +1. And for increasing, decreasing constant, they're always parentheses. So you don't have to think too hard about that. And we'll do our union symbol. And what would our second interval be? 5 to positive infinity. And again, always have parentheses here. You don't have to think too hard about that. Everybody happy there? How many decreasing sections do we have? 2. Good. We have this section here and this section here. So that first section begins at negative infinity, and it goes to negative 3, right? Always the x coordinates. And again, I always start from left to right. Okay? Just like you read a book, you start at the left and you move to the right. So when I look at my intervals or my sections of the graph, I'm always starting on the left and going to the right. That's the convention. Now, I wouldn't mark it wrong if you had like these intervals switched around, because that part doesn't matter. What I would mark wrong, though, is if you had 1, negative 3 instead of negative 3, 1. Just for everybody's. Amy? So what we care about is the x direction of the arrow, right? So because it's the left arrow and it's pointing up, it's kind of like that. But we only care about the x, right? So this arrow over here would be like positive infinity because it's going to the right, and positive infinity because it's going up. But again, all we care about is the x. So again, it's easy to get thrown because you think of the arrows up and down. You have to think about it left and right and up and down, like it's an ordered pair. And if you think about it that way, it's very easy to kind of keep it straight, or easier anyways to keep it straight. You're welcome. Okay, the next section for decreasing goes from 1 to 3, right? Everybody agree with that? And then how many constant sections do we see? 1. And that just goes from 3 to 5. Now, if you take a calculus class later, you're going to redefine what it means for a part of the graph to have 0 slope, which should be equivalent to constant. So in a calculus class, what you'll define 0 slope as is if when we draw a line that's tangent to the graph, so it would intersect the graph locally at just one point. If that tangent line has slope 0, you'd say that the slope of the graph is 0 at that point. But that's going to be something that's slightly different than being an interval that's constant. So if you will end up taking a calculus class, some of you probably will, you'll definitely spend a lot of time talking about slopes of graphs at a single point, which is a weird thing to define because the slope formula requires 2 points. But we're going to kind of alter that definition so we can do it with a single point by talking about the slope of a tangent line. And that's kind of where you're going to be going eventually in a calculus course. But for this course, I would never ask you about that again. I'm just kind of mentioning it as a side. So like if you ever do take a calculus course, you can go, oh, I kind of remember Mr. Kulik mentioned that one day 3 years ago. Sergio. I have not here. Mr. McCaskey's kind of been the teacher for that course as long as I've been here. But he's down to part-time, so he'll probably retire at some point. I don't know who will teach it at that point. He does one of the 2 years. Yep, Ms. Garcia does the first year of it, and he does the second year. Okay, everybody feel okay about this idea of increasing, decreasing, and constant? Not a big deal, right? It's similar to positive, negative, 0. So the hardest part is kind of keeping the 2 straight, right? The last thing I want to talk about today is something called end behavior. And again, I'm going to define this informally because for us, I just want you to be able to kind of look at a graph and tell me about the end behavior and not so much worrying about proving anything with it. But all the end behavior is just describes what the arrows on a graph are doing. So we'll do a couple of examples here to kind of get used to the notation, but in general, it's pretty easy. So if I look at this graph, how many arrows do we see on this graph? 2. I see one here and one here. So we need some way to differentiate the 2 arrows. Let's refer to them as the left arrow and the right arrow. Okay with that? Now when we talk about left and right, what coordinate are we really talking about? The x coordinate, right? I should say correct. Not if I say the left, comma, right, that's unnecessarily confusing. So when I say left arrow, in this case, because that arrow is going to the left forever, we'll say that x approaches positive infinity. That's going to mean the same thing as talking about the left arrow. And what is that left arrow doing? Which way is it pointing, up or down? So points up. Up and down refer to which coordinate? Y. So pointing up means that y goes to positive infinity. So if I wanted to say that the left arrow points up, I would say that as x approaches positive infinity, y approaches positive infinity. Okay with that idea? That's just the notation that we're going to use to describe what we're seeing visually. Okay? Yes?
How is x positive infinity?
Oh, it's not. That's an excellent point. Thank you. Yeah, we're going to the left. The left is definitely negative infinity. If you see me doing things wrong, I really appreciate it when you tell me and let me know. Even if it's a question like, why is that? When I'm wrong, I'm definitely wrong. So I want everybody to take note of that. The x should be going to negative infinity. Woo! I'm glad you were here, because I would have just kept bulldozing along and maybe not even noticed. Somebody would have, I'm sure. Okay, now let's look at the other piece. So that's the right arrow. Everybody's okay with that? So for the right arrow, what are we going to say? Because we're talking left and right. It's x approaches, and then what would it be? Positive infinity this time. And then which way is the arrow pointing? Down. So because it's up and down, we're talking about, we'd say y approaches negative infinity. Everybody okay there? All right. You ready to look at the worst case scenario? As where probably as hard as I would ask you to deal with. Because this is not so bad, right? It's just understanding how to write the notation. Okay. How many of us have seen a graph with these little dash lines on it like this before? Okay, nobody has, that's fine. These little dashed lines are called asymptotes. Not important that you know how to spell that right now. We'll talk a lot about asymptotes later on, especially in second semester. But basically all the asymptote is all an asymptote is a line that the graph approaches but doesn't cross. It's like a barricade. The graph can get up as close as they possibly can to it, but they can't ever touch it. They can't ever cross it. Okay with that idea? Okay. So if I look at this graph, how many arrows do we see on this graph? 4, right? I have one here, 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 and here. So we have 4 arrows to describe, so there'll be 4 end behaviors to describe. Everybody's okay with that? So let's just kind of work from left to right. So if I start here at the leftmost arrow, so we're going to have x approaches negative infinity, right? Because the arrow's pointing all the way to the left. Everybody's okay with that? But here, the arrow isn't pointing straight up or straight down, correct? It's pointing flat to what y value? 2, right? It's kind of going and approaching 2. Is everybody okay with that idea? We can see that. So I'll label this as just like 1, just so it's clear what we're referencing. Now let's talk about this arrow. Here, x is approaching not positive or negative infinity, right? But a specific value of x. That specific value of x is -3, where that asymptote is. Okay there? But here the arrow is pointing down, so the y is going to negative infinity. Is everybody okay with that? Okay. Let's go up here. I'll call this arrow number 3. So again, that arrow is going right up to that vertical asymptote. So we can say x approaches -3. But this time the arrow is pointing up, so we'll say y approaches positive infinity. Everybody so far so good? And then we'll talk about the last arrow here. So here that arrow is pointing straight to the right. So x approaches positive infinity. But y approaches 2. Very good. Now, if you look at this, you should see one little problem here with what we've written. So y approaches negative infinity, or approaches -3, 2 different places, but you're getting opposite y values, which doesn't seem very functiony, right? We're going to the same x value, but we're going to 2 different y values, seems not very functiony, right? Because you have to have the same y value for any given x value. So what we're going to do is we're going to add a little bit of extra notation to indicate whether the graph is going there from the left or from the right, which will allow us a little bit more flexibility in saying, okay, you know, if we're going in from this direction, it's doing this thing, but if we're going from the other direction, it's going the other way. The way we do that is we're going to put a superscript next to those x values. So if I look at arrow number 2, we're approaching x from what direction? The graph is coming in from the left, right? So the left x values are negative. So we're going to put a little negative sign as the superscript there. If I look at arrow number 3, we're going to the x value of -3. We have to follow the graph from the right to the left. Do you guys agree with that? To get on arrow number 3? So if we're coming from the right, that's where the positive values for x live. So I'll put a little positive sign in the superscript there. Everybody's okay with that? We can do the same thing here for the y values. You notice that these two y values are the same, even though the graph doesn't actually have that same y coordinate anywhere. So if I look at arrow number 1, we're approaching the y value of 2 from below. Right? We're coming up from underneath. So below, when we talk about y's, is where the negative y values live. So use a negative superscript. And if we look at arrow 4, we're approaching 2 from above. We're coming down into it. Everybody see that? Above is where the positive y values live. So we can do a little positive superscript there. And that adds a little bit of extra clarity for a situation like that, where you have the asymptotes in there. That's as bad as I would ever expect you guys to deal with, which again, visually is doing most of the work here, right? There's no calculation. You just have to remember the notation and understand like what to do with it. But that's it for, I'll have a homework 2. Now, I goofed up when I made this homework 2, just so you guys know. The page of homework 2 is like the same problems you did in homework 1. You don't need to redo them, okay? So just do the second half of that, where the homework problems are actually different. And then I'm going to put in homework 3 right now. We haven't talked about extrema yet, but we have talked about end behavior. I'm going to put the homework 3 in there. You can do the end behavior part. You're ready to do that. You're not ready to do the extrema part. But I figure since you can do part of it, I'll put it in there. And if you do it, you do it. If you don't, and you wait, it's, it's really not much different. So I figure I'll just put it in there and you can decide what you want to do with it. Okay with that plan? Okay. Are you guys excited that you really have a 3-day week? You know that Thursday's a learn from home day?
Is there a meeting we have to go to on Thursday, or you guys have to?
My plan is I'm just going to post something for my class to work on.
Okay.
And basically review what we've done to this point assignment, which seems like a good use of a time on a day where I don't think anybody needs to try to do anything new. We've been moving, I think, at a reasonable speed to this point. So, yeah, do it, dude. But that's it for today. So.